Hello, and welcome back to a video series on MAT 1033 Intermediate Algebra. My name's Sean Perry. This is video number 28 in the series on scientific notation. You may have noticed in previous videos or with your homework that exponents can get pretty large pretty quickly. For example, 10 to the 2 is 100, while 10 to the 10 is 10 trillion, and 10 to the 100, or a 1 followed by 100 zeros, is a trillion times more than the number of atoms in the known universe. So a very big number, almost ridiculously big, and yet we can write it so compactly. And negative exponents mean division, and division by a large thing is a small thing, so negative exponents can actually get really tiny really quickly. For example, 10 to the minus 2 is 100th, and 10 to the minus 10 is 1/10 trillionth. Now, it's much easier to write 10 to the 10 than it is to write all those zeros. This gives us a useful way of writing very large numbers. Say we wanted to write the number 696 million without all these pesky zeros. This is about the size of the sun if we measured it in meters. What we're going to do is take advantage of the fact that multiplying by 10 or powers of 10 doesn't change the digits, it just moves the decimal around. Notice that in order to move the decimal between the first and second number, the 6 and the 9, I have to move it 8 times. And so what I could do is write the number 6.96 and times that by 10 to the 8th power. This would move the decimal 8 times and give me 696 million. So we want to count how many places we need to move the decimal to get it just past, just to the right of, that first non-zero number. I want you to note that when we write things in scientific notation, you know if a number is big or small very quickly. You just look at the exponent and its sign. Positive exponents correspond to big numbers, in this case, like hundreds of millions. And we can go from scientific notation back into regular notation just as easily, just by moving the decimal but keeping the numbers the same. For example, let's say I had this number in scientific notation, 3.214 times 10 to the 16th power. Now, all I would need to do is move this decimal 16 times. And do I move it to the right or the left? Well, 16 is positive. I want to make this a bigger number, so I move it to the right. Now, after 3 places, we need to keep moving it, but we need to put zeros there to hold place. If I need to move it 16 times and the first 3 moves were taken up by moving it past the numbers, I need 13 more zeros on the end to make this decimal end up in the right place. And so what we wind up with for 3.214 times 10 to the 16 is 3214 and then 13 zeros. Now, putting the commas every 3 zeros, starting from the right, as you do, we wind up with 32 quadrillion, 140 trillion as a number. The exact same process is what we would do for tiny numbers using negative exponents. Let's say I had something like 0.000000000421. This is 421 trillionths. You might notice I don't generally put the leading zero here, although if you like to, that's just fine. What matters is where the decimal place is. Now, how many decimal places do I need to move to bring that decimal just past the first non-zero number, just past the 4, just to the right of it? Well, we can count, and I need to move it 10 places. That's going to be my exponent. And since we started out with a very tiny number, if I wanted to this expression here to be equivalent to this tiny number, this is going to have to be a negative exponent. So we write 4.21, all the rest of the decimals afterwards, times 10 to the minus 10th power. And note that negative exponents correspond to very tiny numbers, in this case like trillionths. Again, if we wanted to go back into regular notation, like say, for example, we wanted to go from 3.021 times 10 to the minus 6. It's negative, so this number is small. I want to move this decimal 6 places, and I want to move it to make this a small number. So moving it this way, one move takes it past the 3, and then I need 5 more moves, 5 more zeros, to put the decimal in the right place, so that in total we've moved it 6 times. So that means that 3.021 times 10 to the minus 6 is 0.000005 zeros and then 3021. which is 3,021 billionths. Now, for multiplication and division in scientific notation, we can use properties of exponents to write that in a slightly different way. We can deal with the 10 powers separately and the numbers separately. Let's see what I mean. So for example, let's say I wanted to multiply 3.21 times 10 to the 14th times 2.1 times 10 to the minus 6. What I could do is rearrange this a little bit. This is all just multiplication. They use the x quite frequently to mean multiplication with scientific notation. No problem. That's just times. This is 3.21 times 10 to the 14 times 2.1 times 10 to the minus 6. And we know that multiplication can be done in whatever order you darn well please. So why don't we group the numbers up front, and why don't we group the powers together? Because taking the product of two powers is easy. 10 to the 14 times 10 to the minus 6 is going to be 10 to the 14 plus negative 6, which is 10 to the 8th. So this exponent part turns into 10 to the 8th. 3.21 times 2.1 is either, practicing your long multiplication, or I guess getting a calculator out if you gotta, is 6.741. So now we have our answer, and it is already in scientific notation here. Notice that we have the decimal between these two numbers. It's just after the first non-zero number. That's important for scientific notation. And then we have the number, its decimals, and then times some power of 10. Scientific notation and, doing multiplication and division with scientific notation is often used by scientists when they deal with large numbers or large and small numbers. So say, for example, here's a fun problem. The sun is about 150 billion meters away. And in terms of meters, an atom of hydrogen is about 0.0000000000005 meters wide. So how many atoms of hydrogen would it take to line up from Earth to the sun? Give or take. I know there's some atmosphere involved, but let's just treat this as a little silly problem. How many of these tiny things do I need to line up to give me this big distance? Now you could do the division, but man, that's going to be a lot of zeros. So what we would do instead is rewrite things in scientific notation. 150 billion, or 150,000,000,000,000, well, that's 1.5, and then 11 moves of the decimal to bring it to here. So that is 10 to the 11th, 1.5 times 10 to the 11th. And this number, which is actually 5 picometers, also requires us to move the decimal, but it's a small number. Moving it 12 times brings it here, so this is 5 times 10 to the negative 12. Notice if there's just one number, I don't really need a decimal or anything like that here. Now, the question, how many of these tiny things fit into this big things, is a division question. 1.5 times 10 to the 11th divided by 5 times 10 to the minus 12th. That's our problem. So let's rewrite our division in our nice quotient form here, and let's see that we can actually deal with the numbers part first and the exponent part separately. For the exponent part, I'm dealing with 10 to the 11 divided by 10 to the minus 12. And the division of these bases to a power is the difference of their powers to the same base. And so 11 minus minus 12 gives me 10 to the 23rd, a very large number. And we would expect that if we divided a big thing by a very small thing. And of course, 1.5 divided by 5, well, we bring this inside, we carry the decimal up, and we wind up with 0.3. So what we get in the end is 0.3 times 10 to the 23rd, but it's not really the end. We're not quite done here. This is correct, but it's not exactly in scientific notation because this is 0 up front. Scientific notation needs the decimal to follow the first non-zero number. So we need to move this guy 1 over. How does that change the 23? Well, what I like to do, because you should know how to write 0.3 in scientific notation, is to just rewrite that in scientific notation, right? How many decimal places do I need to move it? Once. So this is going to be times 10 to the 1, and it's a negative 1 because 0.3 is a small number. So 0.3 in scientific notation is just 3 times 10 to the minus 1. And if we slip that in here for 0.3, what we get is 3 times 10 to the minus 1 times 10 to the 23rd. Now, the product of powers is the sum of their exponents, so we wind up with 10 to the 22, which is about 30 sextillion atoms. All right, let's take some critical notes. Copy this down so I know you watched the video. Here is scientific notation in a nutshell. You'll have a non-zero number, then a decimal, then maybe some other stuff. Then we have a time symbol, often an X, 10, and then a power. If it's bit positive, it's big. If it's negative, it's small. If I want to write a number in scientific notation, I move the decimal until it's in the right spot, I count how many moves, and I put the appropriate power. This was a big number, so this is a positive power. If I want to go the other way and go from scientific notation back to regular notation, I look at how many places I need to move it. It's negative, so this is going to make it smaller. Moving to the left makes the number smaller. So I move that decimal point 3 times. That puts 2 zeros out front, then a decimal. So here's some not so critical notes. You can skip this if you like, but parts of this may be helpful in your science class. Not the whole thing, obviously. I don't know anybody who uses quectometers, but centimeters, surely. Kilometers, definitely. And what they mean are powers of 10 that are either negative powers for very small numbers, notice the decimal moving, making these small, or large powers of 10, so increasing the size of this number. And here we have the exponent that corresponds to that. And here we have the terminology for that. And the prefixes that are used are listed here. Before we do our praxis for the day, I want to make a brief note on calculator notation. Especially the TI calculators will output numbers in scientific notation sometimes. They'll give you things like 1.213 capital E9. And all this means, it's the exact same notation. This E just means times 10 to the power of. So this just means E9 is just times 10 to the power of 9. They mean 100% the same thing. And you can thank all the engineers for using capital E in this way. Okay, so let's work on some praxis exercises for today. Pause the video at this time and give these a shot. Okay, let's see how you did. To move this number into scientific notation, we count the moves here. There are 9 to get it between 3 and the 2 from this ending point here. And so this is going to be 3.204 times 10 to the 9. You can stop after this non-zero number, although you will see in your science class that there are some reasons to put extra zeros on the end. This has to do with what we call significant figures, but I'll let your science teacher tell you about those. For this one, if I want to convert this to scientific notation, I move the decimal until I get between the 2 and the 1, and that's 7 moves. This was a small number, so this is 2.13 times 10 to the minus 7. Here's a couple more. How do I get this to be in regular notation? I have to move the decimal to make it bigger 8 times. That's this guy. I had 3 moves here, and then I need 5 more zeros. What about the minus 6? Well, I need 1 and then 5 more moves. So that puts 5 zeros up front and a 551 on the end. Here is an example of multiplying these two numbers together. I have 3 times 4, that's 12. I have 10 to the 9 times 10 to the minus 5, that's 10 to the 4. And the 12 this isn't in scientific notation yet because the decimal is after the second number here. So I need to write that 12 in scientific notation. 12 in scientific notation is 1.2 times 10 to the 1. Not very useful for those small numbers, but this does help us see how to write it in scientific notation, because now I take 10 to the 1 times 10 to the 4, that's 10 to the 5. Done. A centimeter is 100th of a meter, and a kilometer is 1,000 meters. So when we ask how many blanks fit in a blank, that's a division type question. You divide the large number by the smaller number to see how many fit inside. So what we're going to really want to do is take 1,000 divided by 0.01. Yes, you could type this into your calculator, 100%, no problem. But I want you to see how scientific notation might be used in this case, and in particular, your exponent rules. So what is this? It's 10 to the third. What is this? It's 10 to the minus 2. And what happens when I divide them? Well, I take the difference of these two, but minus 2 is plus 2. 3 plus 2 is 5. 10 to the 5 is 100,000. So there are 100,000 centimeters in a kilometer. All right, that's it for this video. Thank you for your patience and have a great day. I'll see you in the next one. Good luck with your studies.